Hermitian. Not only positive definite, but also Hermitian. Because they will have a non-trivial imaginary part. Now, so this is, I say, the Hubble problem. This Hubble problem, I think, before or later will be solved, and we will have a full parametrization, which is the complete. So this for your question last time, how much is solved this problem? This is missing. This is missing the full parametrization. Now, we still have to when we have considered the second commutation relation of type 2 and the third, what about the first one, which is most important, which the one that gives us, as we will see in a moment, the bosonic interacting Fock space, because it says that the creator commute. So, well, now since the time is very, very short, I will not go into the detail, but I tell you, I say the following fact. The result is very surprising. Also, this was completely surprising for me, is this. From the point of view of constraints, the identity 1 is a corollary of this, is equivalent to this. From the point of view of constraints, not that the two are the same, of course, they are different, they give you different information as a commutation relation. But from the point of view of constraints, they are equivalent. You prove. And this is a little bit longer, but again, once you know the method, to arrive to it took a lot of time. But once you know the method, the proof is not difficult. So we have now captured all the information of the new constraints coming from multidimensionality. These are the new commutation relations, and they are given by these inductive constraints. But the discussion of the inductive construction and so we have discussed the inductive construction of the A0. So suppose I have A0. What is the logic that one would like to follow? So we start from the quantum decomposition. Let me call this QD. Okay, so the logic will be the following. Start from the quantum decomposition. From the quantum decomposition, you know that the P0 is one-dimensional. And since you know also that Phi0 is norm 1, you know the scalar product on 0, which is the Euclidean scalar product. We said already. This is the Euclidean one. Then, let us do, as we did for the one-dimensional case, the first step of the induction. In the quantum decomposition, we know that A minus kills the vacuum. Therefore, the inductive definition of creator will be A dia J restricted on 0 is xj minus A0J0. This means A0J restricted to the space P0. But P0 is one-dimensional. So to give an operator on a one-dimensional, a linear operator is the same as giving a number. And since A0 is self-adjoint, I have an arbitrarity of 1. So in the first step, we know this arbitrarity. When n is equal to 0, the arbitrarity is 1. We have one parameter arbitrariness. We can choose arbitrarily the real number in correspondence to what was the Favart lemma. Huh? So the A0 restricted to A0 is arbitrary. Suppose that I have now fixed my choice of A0, but then I have the creator. If I have the creator, I obtain algebraically the creator is well defined as a linear operator. So the range is well defined. And I have that A daga J0 image of P0. This, by definition of, of course you have to take, if you remember, you have to take, not exactly this, but you have to take the linear span. Linear span of this. When J varies from 1 to D, this is, we know, but in this case we define to be P1. You see, now we have not the state, so we don't know which are the orthogonal polynomial. The difficulty, we want to construct this space, this Pn, and a posteriori we will recognize that they are the orthogonal polynomials for some state that we are going to construct. Okay? So we have defined the P1. P1 is well defined as a vector space. And now, in order to do the induction, we have to define what? We have to define the other cap operator, because this has given AJ0, but now I have to define the scalar product on P1. I know that the scalar product, by my definition, the scalar product, I know it is uniquely defined by the kernel omega tilde. You remember? If you put this n equals 0, the scalar product on the one space is uniquely defined by the omega tilde. So to assign a scalar product on the space P1, I must give a kernel on the space P0, but P0 is one-dimensional. So a kernel must be a multiple of identity. So a kernel is a scalar, and I know already this from this. Okay? So what I have to do? I have to choose. Here I know that the imaginary part is given by this. But you see, the
P1 is one dimension. What are the parameters? P1 it's one dimension.
P1 is by definition this. Is the range of a dagger.
P0 is one.
P0 is one dimension.
P1 is d-dimensional.
P1 is d-dimensional.
Yes.
D-dimension. Up to set of vector measure 0, but the algebraical is d-dimensional.
And then you are using some logic that since it's one dimension.
And I want to give a, but it's a kernel. So it's two indices. So it's a positive definite kernel, it's a scalar product. To give a scalar product on a d-dimensional space is the same as giving a positive definite matrix, which will be the positive definite matrix with respect to the Euclidean scalar product. Okay? This is clear, because if I have a my space is isomorphic to CD. It's clear. So my kernel, my creator AJ goes from P0 to P1. Now, by definition, the elements of P1 are linear combination of this. So the scalar product is uniquely determined by scalar products of this form. Okay? But these scalar products are since I minus I plus is gradation preserving, this is some scalar. Well, I am now, well, let me call beta, but because this is what we have called omega tilde 1 jk, and this we can call beta 1 jk. Now, a priori, this could be a complex number, okay? But we know that it must be real from lemma 2. So, we know that this is real. So we take a positive definite kernel, which this defines a scalar product on CD. So this beta 1, which is the matrix, is positive definite. Therefore, it defines a scalar product.
Positive definite with real entries.
Yes. Real entries. Positive definite with real entries. This real should be followed because it will give you restrictions on how to choose. At every step, we have to choose a scalar product. You see, we are doing the first step of the induction. So it's very important to keep the constraints. You should not lose constraints, otherwise the reconstruction theorem may fail. So, and the scalar product will give simply this. Just the density, roughly speaking, the matrix density with respect to the standard Euclidean product. And now, since you use this isomorphism to bring this scalar product to a scalar product here. You see, why I could do this? Because by lemma 1 I know that I have no imaginary part of the kernel. Otherwise, I have to add the imaginary part, but I know that this will not harm, doesn't introduce constraints, because the sum of any positive definite plus skew adjoint is still positive definite. So no constraint. Okay? So you see, the other steps of the induction, I will tell you later. Why these steps are important? Because you see, this lemma, these two lemmas, all go by equivalence. So if we follow this, we automatically satisfy these two conditions. Therefore, we are automatically assured that the commutation relation are true. And from this, from a theorem that I will show you next time, we know how to reconstruct